Recent videos we've been taking a look at waves, and now I specifically want to focus a little more on sound waves so we can see how that interfaces in with the sense of hearing. So I'll start with a quick reminder of how sound waves work. Remember, they are a longitudinal wave, so this means that the waving, the simple harmonic motion of the air particles is parallel slash anti-parallel with the direction of propagation. This leads to areas where the air gets piled up. We call those compressions. And areas where the air is a little less dense than normal, we call those rarefactions. Just as a little bit of a preview for when we start looking at light waves in future treatments, not this series. If you erect a geometric ray that is perpendicular to the wavefronts, that cleverly gets called a ray, and we'll see that these, especially in the context of light, that these rays can have very particle-like behavior. But we don't really need to worry about that now. That was just a little bit of added bonus. So anyway, the distance between successive compressions or successive rarefactions or whatever, that will be the wavelength. And remember, the symbol for wavelength is a lowercase Greek letter, lambda. Okay. Now, how things differ with sound waves is that they can actually propagate in 3D in a meaningful way. And so when physicists draw diagrams of the propagation, well, since a lot of us aren't gifted with a whole lot of artistic skill, our usual approach is that we draw things in cross-section. So it turns out that most sound sources will emit a spherical wave, or at least a portion of a spherical wave. The longer the wavelength, typically, the more completely spherical it is. So if we take a look at a spherical wave, here I'm going to be drawing the wave fronts in blue. So let's say the source of our wave is right here at the middle, and at this exact moment it's emitting a wave front. Then what we can do is we can draw concentric circles around it, and really, even though I'm drawing circles, you should be understanding that we're looking in 3D cross-section and that these are actually spherical shells. So the wave fronts are spherical shells in 3D around the source of the wave. And the spacing between these wave fronts is a wavelength. So you can think of it as, say, a compression here, compression here. So that would be the separation. Now, one thing to notice is that when you get really, really far away from a spherical wave, if you look at a small fraction of the spherical wave, like let's say right over here, it starts to look approximately flat. And so for ease of thinking about things, we often talk about plane waves, which is what I drew already. And here when we draw a bunch of lines here, what we're really thinking is that these are planes in 3D. And again, they would be separated by the wavelength. So here our direction of propagation would be like this. Here we're propagating radially outward in all directions. So if you're close to a source, it makes And it makes sense to model it as a sphere, the wavefronts as spheres. When you get really far away from the source, it makes sense to model them as planes. If you're in between, well, I'm really sorry, the math of that gets really ugly. Plane waves, or at least excellent approximations to plane waves, can also come from other sources, again in the context of light, which a future treatment would explore. A laser is a very good source of waves that are almost planar. So getting on the way to thinking about how to characterize the, at least just even how loud something sounds, we can start by defining the intensity of a wave. So if you think about it, in order to hear something, the air molecules in the sound wave collide with your eardrum, do mechanical work on your eardrum, and then that mechanical work ultimately gets converted into electrical impulses that get transmitted through your nervous system and into your brain. But the point is that you actually, in order to hear something, the wave has to do mechanical work on the listening device. It's exactly the same deal for a microphone. In the case of microphone, it's either exactly modeled after the ear, where you've got some sort of a flexible membrane, and as the air molecules strike it, it causes that membrane to vibrate, and then you can measure that electrically, the vibrations electrically. Or another classic one is to have a sort of like a cylindrical puck filled with carbon particles, and as you speak it causes the carbon particles to jump around, which changes the electrical property of that little hockey puck like thing, or that little puck shaped thing, and that generates the electrical signals to represent the wave. But either way, the sound waves striking a microphone are either doing mechanical work on some sort of a flexible membrane, or are colliding with carbon particles, causing them to jump around. So since we're doing work on it, what's going to matter is how much work we can deliver per unit time. Now, we've already observed that waves carry energy. So if we look at, say, this portion of a wavefront here of area A, and it's propagating out like so, we can define the intensity of the wave, I, to be the power that the wave carries over the area. And this sort of makes some sense, because the only power of the wave that counts, say, for your ear, is going to be that chunk of the wave that actually strikes your eardrum. So we need to be able to talk about a energy transmit per unit time per unit area. So the units of intensity are watts per square meter. Now, so we can think about how a wave propagates out. So let's look at a couple of different wavefronts coming from the same source. So let's say this is my source right here. I've got a wavefront that's supposed to be a circle centered on the source. Let's try that again. Yeah. Let's say it's radius R1 there. And then it's some greater distance. Again, that's supposed to be a circle centered at the source. We'll say that that radius is R2. And again, you are looking at spherical wavefronts. Well, at any time, we can describe the intensity of the wave, because we know that over the entire wavefront, whatever the power was, it had to be equal to the power delivered by the source. And we know what the surface area of a sphere is. Since these wavefronts are spherical, we can just look at the entire wavefront as our area of interest. And we know that that area is 4 pi r squared. This gets called the inverse square law. And it just says that the intensity of the sound falls off as the square of distance. So as an example of that, let's say that you're standing, that this is a subwoofer right here, and you are currently standing 5 meters away from it, like so. You're going to hear some sort of intensity, I1. What I'd like to know is how far away will I need to stand from the subwoofer so that the intensity is now a quarter of what it was when I was 5 meters away. So we need to figure out this distance, R2. Now the reason I mentioned a subwoofer is subwoofers have very long wavelengths of sound. And it turns out that for most sound sources, the longer the wavelengths, the more spherical the wave, the more complete of a sphere the spherical wave is. In the case of a subwoofer, it's almost perfect. So that's why in this example I'm using a subwoofer. Well, this would be an example of a scaling problem here. So we can say at location 2, the intensity there will be equal to the power of the source, whatever it is, over 4 pi r2 squared. We can divide both sides by I1. On the left, we'll express I1 as just, I1. And on the right, we will express that as the power of the source over 4 pi r1 squared. All right, cancel, 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 cancel. We end up getting r1 squared over r2 squared, which is the same difference as r1 over r2 squared. All right, so if we take the square root of both sides, we get r1 over r2 is equal to the square root of I2 over I1. So then we can rearrange this to get that R2 is equal to root I1 over I2 R1. We were told that I2 was a quarter of I1. So cancel, cancel. So this is the square root of 1 over a quarter. 1 over a quarter is 4. Square root of 4 is 2. So we get that this is 2r1, which is 2 times 5 meters, which is 10 meters. All right, and we could follow the same sort of logic for other proportions. So for instance, if something was 10 times farther away from the source, the sound intensity would be 1/100th what it was before. Now ask yourself, is that what you actually hear if you get 10 times farther away? Think about it. If you stand a meter in front of a speaker and then you go to 10 meters in front of a speaker, it probably only sounds a little bit quieter. It doesn't sound 100 times quieter. This is an artifact of how we perceive sound. So this is a biological issue. And to model this, we use what's called the sound intensity level. So The symbol for that is a lowercase Greek beta. So to draw one of those, something like that. The sound intensity level is defined to be 10 decibels, more on that in a second, times the base 10 log of the sound intensity over some reference level. So a decibel, again, if you follow this through, there are no physical dimension here. So this is a symbol to tell us we're in sound intensity level. It's not a proper unit. And also something to super duper watch out for is that it's a base 10 log, not a base E log. Almost every logarithm in physics, except for this one and one related to stellar magnitudes, is base E. This one's base 10, so be super duper careful that you're punching the LOG key on your calculator if you need it, not the LN calculator. That will throw you off. Now this reference intensity level is usually and like this is what's referenced in noise ordinances and stuff like that, 10 to the negative 12 watts per square meter, which is the threshold of human hearing. This is if you take people who haven't been exposed to much in the way of loud sounds, have healthy ears, put them in one of those special soundproof rooms, and then you start playing very quiet sounds and tell them to lift their finger when they first think they might have heard something. And then you take an average of that across subjects. That turns out to work out to be about 10 to the negative 12 watts per square meter. Now, since this is a logarithm, base 10 logarithm, if something were at the sound intensity, at the threshold level, so something, if you were hearing something at 10 negative 12 watts per square meter, this ratio would be 1. The log of 1 is 0. And so at a sound at the intensity that is at the reference intensity level would have an intensity level of 0. If something had an intensity that was 10 times greater, then the logarithm, we would be taking a logarithm of 10, and the base 10 log of 10 is 1. So that would be perceived at 10 dB. If it were 100 times greater, that would be the logarithm of 100 in base 10, which is 2, so that would be 20 dB, and so forth. Now 10 dB, just to give you some reference, would be a person breathing about 3 meters away from you. 20 dB would be somebody whispering about a meter away. When you get up to 10 to the negative 9 watts per square meter intensity, that would be a ratio of 1,000. The log of 1,000 is 3, so it'd be 30 dB. That would be if you were in a physical classroom taking a test and nobody was talking. To get to some other extremes, most home stereos, if you crank it all the way up, will have a maximum output on the order of about 1/10 of a watt per square meter. So a tenth of a watt per square meter divided by 10 to the negative 12 is 10 to the 11, which is 11. So I guess that does give some proper meaning to the idea of churn it up to 11. But anyway, you'd then have to go and times it by 10 to get 110 dB. A rock concert is 120 dB, and your ears start to hurt at 10 watts per square meter. which would work out to be 130 dB. So that's the threshold of pain. If you're below the threshold of hearing, then you'll have an intensity that's less than 10 to the negative 12 watts per square meter. And when you take the logarithm of that, that'll be a negative number. Now, just as a quick aside, in this treatment, this is the reference intensity level I'm always going to use. Stereo manufacturers tend to use a different one. They have imagined a certain standard speaker, and they say that if you put your sensing equipment 1 meter away from the speaker, that at that point, if you are producing a wave of 1 watt per square meter, that's the reference intensity they're using. So in that case, anything above 1 watt per square meter is heading rapidly into threshold of pain territory. And that would give you positive logarithms, and anything that would not hurt the ears would be giving you, because it would be less than that reference intensity level, would give you negative logarithms. So if you have a stereo where when you turn the volume knob and you just see negative numbers, and as you crank it up, the negative numbers get closer to 0, it's because they're using that standard for the reference intensity level. But in most biological and legal application, 10 to the negative 12 watts per square meter is the go-to number, so I'm going to be using that. So let's just work a couple examples of this one real quick just to get a feel for it. So let's say you had a sound intensity level of 30 dB, and you wanted to, let's go and find what the corresponding sound intensity is in watts per square meter. Okay, so we have beta 10 dB log base 10 I over I naught. So the problem is the intensity we want is stuck inside the log. So our strategy is going to be first to divide through by the 10 dB to at least get the log by itself, and then we'll have to take the anti-log of both sides to start peeling the I out. So we'll say, all right, log base 10 of I over I naught is equal to beta over 10 dB. All right, and we remember from logs that the inverse operation, so the inverse operation of taking a log is to take 10 and raise it to that thing's power. So 10 to the log 10 of x would just be x, and also log base 10 of 10 to the x is also x. So using that, we're going to say this is 10 to the log base 10 of I over I naught, and this would be, to keep it consistent, we got to do the same thing both sides. We would have to say this is 10 to the beta over 10 dB. All right, now 10 to the log 10 just is going to leave me with I over I naught. And then we get that I is equal to I naught times 10 to the beta over 10 dB. So in our example, it was 30 dB. So our reference intensity level was 10 to the negative 12 watts per square meter. This would be 10 to the 30 dB over 10 dB. And although the decibel has no physical dimension, you should always feel good when they cancel inside of power. So this is 10 cubed. So 10 to the negative 12 times 10 to the 3 is 10 to the negative 9. Remember, you just add exponents. So this is 10 to the negative 9 watts per square meter. Let's just, for completeness sake, take a look at what it would be. So we'll just repeat this for what if beta were equal to negative 25 dB, what would be the sound intensity level then? Well, we know it would, since beta goes negative here, we know that I will have to be less than 10 to the negative 12 watts per square meter. So let's try to follow that through. Well, fortunately, the analysis is identical, so we can just plain steal that result right there and use it again. So we can say, all right, I then will be equal to 10 to the negative 12 watts per square meter. And then this will be 10 to the negative 25 dB over 10 dB. So this will work out to be, now we are taking 10 and raising it to the negative 2.5 power. So to access that in your calculator, that won't be the EXP key on your calculator. It'll be the 10 to the X key. So if we do that and times it by 10 to the negative 12 watts per square meter, you should get 3.16 times 10 to the negative 15 watts per square meter. Alrighty, in the next video we'll take a look at the Doppler effect, which is those shifts in frequency that you hear because either the thing making the sound or the thing listening to the sound is moving. Catch you in the next one.